right? So the thing is, to go for some any other basic modules, we should know the basics of logic gates like and, or, not, NAND, NOR, okay, and then XOR, XNOR, and the function of these logic gates. So here, with starting with this module 2, let us uh, understand what is a decoder, right? Basically, decoder is one IC integrated circuit, or it can be built by using a basic logic gates also. Decoder is a combinational logic circuit which is having n number of inputs, which is having n number of inputs, and it is having 2 raised to n outputs. It is having 2 raised to n outputs. Okay, here it has been written, you can see that it is a circuit which is having n number of input lines and a maximum of 2 raised to n output lines. Okay, say for an example, however, I will not be having a 1 bit decoder. I'll be having a minimum of 2 bit input and decoder. So if n is equals to a minimum of 2 bits, then the output will be 2 raised to n, that is 4 outputs. Okay, so this is a decoder circuit which is going to give me 2 raised to n outputs. Now what is the use of this decoder? Main basically, this decoder is used in communication parts. Okay, communication parts. There is one more opposite function is there, which is also called as encoder, which is an opposite function of decoder that we will see later. But right now, decoder is basically used in communication methods or communication part. Okay, as well as this decoder is also used in CPU for data fetching purpose, data transmission purpose, as well as this decoder is also used in selecting a particular channels or selecting a particular memory address in the RAM or ROM, in a memory devices. Okay, so where all the things that the decoder circuit is going to be used, one thing in a memory devices, right? So that to select a particular uh, section or a particular memory address, then it is used in a communication parts, it is used in a data transmission section in a CPU. Okay, so these are the applications of this decoder. Then let us now see how it is going to function. So one thing here is, uh, this decoder will be having one more input which is called as enable input, E, enable. Okay, so when the decoder is enabled, when the decoder is enabled, on that time only the outputs are going to be activated. Activated means they are going to be worked, they are going to be used only if enable is equals to 1 depending upon the signal. Okay, so if enable is equals to 1, all these outputs are going to be activated. If enable is equal to 0, it means we are not enabling the decoder to function. So whatever the input I give, that will not reflect at the output. Understood? Whatever the input I change here, the output will not be changed. It will not be altered, or it will not be affected when the enable input is 0. Now, when enable is equal to 1, then only the outputs are going to be altered. That is, the outputs are going to be activated based upon this number of bits, input bits. Okay, so as we have a in this diagram, we have a two bits here. So number of inputs are n equals to 2. So suppose if I have a 2 inputs, I'll be having 4 outputs. Okay, so what are the outputs mentioned here? Y0, Y0, Y1, Y2 and Y3. These are outputs. These are inputs, right? So a simple decoder will be having 2 inputs and 4 outputs. This can be increased. It can go up to any number of inputs, and yeah, that 2 raised to n number of outputs. So for an example, another one we have 3 inputs, which will be having 8 outputs. So this decoder is called as 3:8 decoder. As here we have written 2:4 decoder or 2:4 decoder. Okay. So here the output, one more important thing is the output of this decoder, outputs of this decoder are always a min terms. Okay, for n input variables, whatever may be the variable, the output of this is going to be a min term. Say suppose now, okay, I'll go to the truth table here. Okay, so this is a truth table of the decoder. The decoder is explained with this truth table. Okay, so what are the things this truth table is having now? Enable pin, this is the input, and another 2 inputs, A0 and A1. Okay, now these are the outputs, Y0 to Y0, Y1, Y2 and Y3. Now if suppose the enable is 0, whatever the input may be, it is a don't care. So output always be 0. This cannot be altered. It will always be 0. No output is selected here. Will not get any output. Now, if I make enable high, it means I'm making the IC to be functioning. So now the inputs, based upon the inputs, the output are going to be changed, altered. So as it is a combinational logic circuit. So combinational logic circuits, always what will happen? The output is depending upon the input, present input, right? So here what will happen? For 0, 0, the line Y0 is going to be activated. As it is 0, 0, out of 4 outputs, only 1 output is going to be selected. If based upon this input 0 and 1, then the second output is going to be selected. So whatever the value that I'm going to put here, that is going to be transmitted through the second output. Then if I select, if I give an input as 1, 0, then the third output is going to be selected, and then and when I put it as 1, 1, at the input, then I will get the fourth output is going to be selected, right? Say suppose, okay, with a simple example, I will tell you. Uh, Here I have four LEDs connected at the output side. This is one LED. This is another LED. One more LED. Another LED. Okay. So this is Y0, Y1, Y2, and Y3, Y4. Sorry, Y3. This is Y2, Y1. This is A and B. This is enable. Now, if this is 1, so whatever the input I'm going to change, that LED is going to be selected. Suppose if I make 0 and 0, it means I will be having the LED, why not LED is going to be activated or it is going to be turned on. Okay, suppose if I make it 0, 1, then Y1 is going to be turned on. This is 1 0, that is 3, that is Y2 is going to be turned on, and when it is 1 1, Y3 is going to be turned on. If I want to turn on any one of these LEDs, I might be used 4 switches, but here by using only 2 inputs, I am controlling 4 outputs. Understood? I am controlling 4 outputs by using only 2 inputs here, 2 switches. So internally it will be having a AND gate logic functions and AND gate or NAND gate logic functions that we will see in the next. Okay. So this is what the function of a decoder. And as it is been mentioned, the output is going to be, the output of this decoder is going to be a min term. It is represented in terms of min terms, right? So here the whenever, so here we have a output, here we have output, and here as well as here, right? We have output is generated here. Now for this 0001 0001, to get Y0 output, to get Y0 output, what is the input here? The min term of this input that is represented in min terms are A1 bar and A0 bar. Here it is A1 bar and A0 bar. So in min terms, what will happen? The 0 is represented as the complement of that variable. Correct. Now, if I go for the second output here, Y1 is activated. So Y1 is equals to E into, even enable is also there, right? E dot A1 bar dot A naught, right? This expression, this min term. Then for this, it is going to be E into, that is enable is always, then A1, then A naught bar, this one. And for the fourth, it is E dot A1 dot A naught. Y3 is equals to this one. So these are the Boolean functions, that is the minterms that we are going to get from this truth table, right? So based upon this functions, now we are going to implement these functions using AND gates. Okay, let us see how it can be done. So this is a model of AND gate which is designed for a 2:4 decoder. 2:4 decoder, right? So here, let us consider E is a continuous line for all the AND gates. Correct. So as we have got here, there are four expressions, four Boolean functions that we have got. In every expression, we have the variable E, and that should always be equal to 1, right? So here, E is always directly connected to all the four functions. This is one function, this is one function, this is y1 function, and this is going to be y0 function. Okay, so to get all these functions, we require E. If suppose E is 0, say any one of the input of AND gate is equal to 0, always the output will be 0. Correct? So this is according to the truth table. Right? So E is directly connected to all of the functions. Now here, in this expression, we have A0, A0 bar, A1 and A1 bar. Here it is, A1 bar, right? So to implement that, we are going to have a NOT gate here, NOT gate for A1 and one more NOT gate for A0 and direct lines. So to get Y0, what is the expression? It is E dot A1 bar dot A0 bar, right? So here E is connected here, then A0 bar, A is inverted with this NOT gate, then it is connected to this Y0 AND gate. I'll number this AND gate 1, AND gate 2, AND gate 3, and AND gate 4. Then this Y0 will be having A1 bar also. So this AND gate is going to produce E dot A0 bar dot A1 bar. So that will be whenever E is equal to 1 and inputs are 0, 0, only the Y0 line is going to be selected. Okay. Then now the same is to get Y1 output. What we have a Y1 output here, E dot A1 bar A0. E dot A0 bar A1. E dot E is multiplied, then in A1 bar A1 bar A0, A1 bar, and then A0, right? So all are connected to the AND gate, the second AND gate, to get the output Y1. Then what we have, E is equal to 1. Then what is Y2? Y2 is A1 A0 bar, A1 A0 bar, A1 A0 bar. So here y, sorry, E is connected to the AND gate 3. Then A1, A1 is directly connected to the third AND gate, and A0 bar. A0 is here, then here it is going to be connected A0 bar through the NOT gate, then third AND gate, right? So this is Y2 output. Then for Y3 output, this is also 1, this is also 1. Okay, so E is also connected here. Then A1 is directly connected. Then A0 is also directly connected. Okay, so this is how actually it is going to functioning. Along with this, we have some of the ICs, integrated circuits of these decoders, like 74139 and 74138, which is a 3:8 decoder. 3:8 decoders. So therefore here all the minterms are implemented by using an AND gate, right? Now similarly we have 3:8 decoder and 4:16 decoders. So for example, 3:8 decoder and 4:16 decoder. That is 2:4 is equal to 16. Okay. So let us see an example of this 3:4 decoder. Now this is Y0, Y1, Y2, Y3, Y4, Y5, Y6 and Y7. Okay, so this is 3 to 8 decoder. Okay, which will be having 3 inputs, A, B and C. Then it will be having one enable input. Okay, so in between this integrated circuit will be having a number of AND gates implemented on it, so to produce whatever the input is going to be changed. So when 0 0 0, the input is 0 0 0, the line Y0 is selected, so this will become high, or else and rest all are equal to 0 0 0 0. Then when this is 0 0 1, then the switch is connected towards the output 1, Y1. So this will become 1 and rest all are equal to 0 0 0 0. Then it goes on. So for 1 1 1, the switch is directly connected towards the Y7, and this will go high, and all other values or other outputs will remain 0. And only when these are going to be function, only when enable is equals to 1. So for this also, as we have written an expressions boolean functions for the 2:4 decoder and implemented and we have implemented a 2:4 decoder in terms of AND gate. The same way we are going to implement the 3:8 decoder as well as 4:16 decoder. Okay, and Now directly we are getting it as non-inverted outputs. As we have uh, A and B and C, non-inverted inputs, will be having non-inverted outputs. Some of the decoders are providing us inverted outputs. Inverted output means, say, suppose um, I'll take a simple example of this 2:4 decoder only. So suppose this is A and B, and output is going to be Y naught, Y naught with bubbled outputs Y1, Y2 and bubbled Y3, and we have enable here. Okay, so in this case what we usually get is the output is a function of A, B, that is going to be M dash, that is M bar. Whatever the outputs that we are getting here, they are inverted outputs. They are inverted outputs. Say when it is 0 and 0, Y naught has to be equal to 1 and rest all are 0, 0, 0. But this inverted decoder will give me Y naught equal to 0 and all other outputs are equals to 1. Okay, so when it is 0 and 1, y1 is equal to 0 and rest all are 1, 1 and 1. And when it is 1, 1, y3 is equal to 0, rest all are 1, 1 and 1. So for this type of decoders, instead of implementing it by using a simple AND gates, we are going to use NAND gates. We are going to use NAND gates. Say for an example, here why not? I'll put a bubbles here. See, bubble means it is a knot. The only difference between the previous decoder and this decoder is the output is here is bubbled output. Bubble, when I place a bubble in between these lines, then it is a inverted, right? So as we have for a NOT gate, what we have here, we have a bubble here. So to represent this, we are putting a bubble here so that to represent that line as a Y bar. Okay, so this is going to be implemented by using NAND gates rather than AND gates. So using NAND gates, right? Hope you have understood. Even the time is going to be end now in another 2-3 minutes. So just type in the chat box whether you have understood or not, or you have any queries. Any queries or anything not understood? Akshata, Kapila, Asif, Nida, Praful. No reply.